Welcome to my tutoring session in chemistry. The current video is part 4 of the 7-part series in Hplc. I'll begin the video with a detailed explanation about the general features of instrumentation in Hplc setup. This will be followed by stationary phase and mobile phase used in Hplc that are of polar and non-polar nature. And later in the video, I'll explain the normal phase and reverse phase chromatographic separation in Hplc technique. There are two major Hplc techniques commonly employed for carrying out the separation of the given sample mixture into individual components. They are normal phase Hplc technique and reverse phase Hplc technique. In the normal phase Hplc technique, the stationary phase used is polar in nature, for example silica column, while the mobile phase used is non-polar in nature, for example hexene. In case of reverse phase Hplc technique, the stationary phase used is non-polar in nature. The two commonly used non-polar stationary phase columns are C18 and C8 columns. The number 8 and 18, it indicates the number of carbon atoms in the hydrocarbon chain of the non-polar stationary phase. While the mobile phase is polar in nature, some of the polar solvents commonly used in reverse phase Hplc technique are water, methanol and acetonitrile. In the normal phase Hplc technique, the column is tightly packed with a polar stationary phase. For example, in case of silica column, the column is tightly packed with a polar stationary phase, where the stationary phase particles bear a polar silicon group, where the hydroxy group is covalently bonded to silicon. The polarity of the stationary phase is because of the polar hydroxy groups that is covalently bonded to the silicon of the stationary phase. And through this tightly packed stationary phase that is polar in nature, a non-polar mobile phase like hexene flows through the column under high pressure. So there is a pressurized flow of non-polar mobile phase to the polar stationary phase in case of normal phase Hplc technique. Now when the sample mixture is injected into the column via the multiport valve, the components of the sample mixture travel through the column along with the mobile phase, and the relative speeds at which the components of the sample mixture travel depends on their relative affinities towards the polar stationary phase. The polar molecule, it strongly interacts with the polar stationary phase via hydrogen bonding and dipole-dipole interaction, and therefore it is retained for a longer period of time in the column and hence eluted later. While the molecule of intermediate polarity, it interacts moderately with the polar stationary phase, while the non-polar molecule, it weakly interacts with the polar stationary phase and hence it elutes out of the column along with the non-polar mobile phase. Now the rule of thumb is like attracts like. Non-polar molecules will have greater affinity for the non-polar mobile phase and interacts via van der Waals interaction or attraction and are eluted faster. While in case of reverse phase Hplc technique, the column is tightly packed with non-polar stationary phase, which could be either C8 or C18 material. Now the number 8 and 18, it indicates the number of carbon atoms in the hydrocarbon chain. In case of C18 column, you find silica bonded octadecyl group. So the octadecyl group is a long hydrocarbon chain, aliphatic chain constituted by 18 carbon atoms. And this long hydrocarbon chain, it confers non-polarity to the stationary phase. Now C18 column in comparison to C8 column is non-polar in nature because of the number of carbon atoms. So C18 column constituted by 18 carbon atoms, while in case of C8 column it is constituted by 8 carbon atoms. Through this non-polar stationary phase contained in the column, it is tightly packed, a polar mobile phase flows to the column under high pressure. Now some of the commonly used polar solvents for HPLC are water, methanol and acetonitrile. And when the sample mixture is injected into the column via the multiport valve, the sample mixture flows through the column along with the mobile phase, and the relative speeds at which the components of the mixture travel through the column depends on their relative affinity towards the stationary phase as well as the mobile phase. Non-polar molecule, it strongly interacts with the non-polar stationary phase via van der Waals interaction or attraction, while the molecule of intermediate polarity interacts moderately with the non-polar stationary phase. So in case of molecule of intermediate polarity, it interacts equally with both the non-polar stationary phase as well as the polar stationary phase. While in case of polar molecule, it weakly interacts with the non-polar stationary phase and hence it is eluted out of the column. So it is interacting strongly with the polar mobile phase. So rule of thumb, what does it say? It says like attracts like. Polar molecules will have greater affinity for the polar mobile phase and interact via hydrogen bonding or dipole-dipole interaction and hence are eluted faster. Now why a high pressure is required inside the column, or why there is pressurized flow of the mobile phase? The reason is the column is very narrow. It is around 2 to 5 millimeters. That is, the internal diameter of the column is around 2 to 5 millimeters. The column is very narrow and the particle size of the stationary phase is very small. It is around 5 to 20 microns. And the stationary phase, the small particle size, it is packed tightly into the column. So all the three factors, small particle size, tight packing of the column in stationary phase, as well as the narrow column, all these three factors operate together and it offers a greater resistance to the flow of the mobile phase. So smaller the particle size, greater the surface area. And that is one of the advantages in case of HPLC separation. So smaller particle size offers greater surface area and therefore the surface contact with the components of the sample mixture will be more. And hence the resolving power of the technique is more. And therefore the technique is named as high performance liquid chromatography because of the high performance and high resolving power as compared to the conventional column chromatography. And it's also called as high pressure liquid chromatography because there is pressurized flow of the mobile phase. And the components of the sample mixture, they travel at varying speeds inside the column along with the mobile phase. And the speed at which they travel depends on their relative affinity towards the stationary phase. And therefore the operating pressure is around 1000 to 8000 psi. Now in case of reverse phase HPLC column, the stationary phase is a silica particle with bonded hydrocarbon chain. Now here's the structure of a silica particle, and the air-like structures that is protruding outside the surface of the silica particle is the hydrocarbon chain. So you find the bonded hydrocarbon chain onto the silica particle. So in case of C8 column, it is silica bonded octyl group. And in case of C18 column, it is silica bonded octadecyl group. So of these two columns that are widely employed in the reverse phase Hplc column, the C18 column is more nonpolar because of greater number of carbon atoms. So the number 18 indicates the total number of carbon atoms in that aliphatic chain. So 18 carbons in case of octadecyl column, and in case of octyl column, the aliphatic chain is constituted by 8 carbons. And in case of normal phase HPLC column, the stationary phase is a silica particle with a bonded hydroxy group. Now here's the silica particle structure, where you see the silanol groups covalently bonded to the silica particle. Now the polarity of the stationary phase in case of normal phase HPLC is because of this polar silanol group with a polar hydroxy group. So in case of polar silanol groups, you find that silanol is bonded to a hydroxyl group. And the polarity is because of the hydroxy group, that is highly polar in nature. So in a normal phase HPLC column, the polar stationary phase is tightly packed into the column, and the polarity conferred to this stationary phase is because of the silanol group. And through this stationary phase that is polar in nature, a non-polar mobile phase, it flows through the column at high pressure. So here we have a polar stationary phase, for example silica column, in case of normal phase HPLC technique. And the polarity is because of the presence of silanol groups. A non-polar mobile phase, it flows through the column under high pressure. Now some of the compounds that can be separated that are of medicinal interest are testosterone, amphetamine and naproxen, that are non-polar in nature. Now it is not totally non-polar or completely non-polar. It is slightly polar because of functional groups like keto group, hydroxy group, amino group and carboxyl group. In case of testosterone, you can find two polar groups, keto group as well as the hydroxy group. In case of amphetamine, polar amino group is there, and in case of naproxen, you find the terminal polar carboxyl group. So rule of thumb is like attracts like. Non-polar molecules will have greater affinity for the non-polar mobile phase and interact via van der Waals attraction and are therefore eluted faster. Non-polar molecules elute faster from the column along with the mobile phase. Now the non-polar molecules interact weakly with the polar stationary phase via hydrogen bonding or dipole-dipole interaction. So it is not that the non-polar molecules interact only with the non-polar mobile phase. There will be a little bit of weak interaction with the polar stationary phase. That will be by hydrogen bonding or dipole-dipole interaction. Because these molecules, they have polar functionalities, like in case of testosterone, you find the polar keto group and hydroxy group that are capable of hydrogen bonding with the polar stationary phase. In case of amphetamine, you find the polar amino group that is well capable of hydrogen bonding with the polar stationary phase, that is silanol groups. And in case of naproxen, you find the carboxyl group that is very well capable of hydrogen bonding with the polar stationary phase, that is hydroxyl group of the silanol group. Now in case of reverse phase HPLC technique, the stationary phase is non-polar in nature. Now here in this diagram, what you see is that of a C8 column, the structure that is mentioned here. Now in case of reverse phase HPLC technique, we employ a non-polar stationary phase. A non-polar stationary phase is prepared by chemical treatment of polar silica layer with selenizing agents by a process called selenization. During this selenization process, the polar hydroxy groups are completely blocked by a non-polar octyl or octadecyl group. For example, when you treat the polar silica layer with chlorodimethyl octylsilane, the polar hydroxy groups, they get blocked. They chemically interact with the selenizing agent, that is chlorodimethyl octylsilane, and after the chemical reaction you get a chemically bonded phase. And here in the C8 column you can find that the polar hydroxy groups are completely blocked. The hydrogen atom is removed during the reaction, making the stationary phase non-polar in nature. Now here in this non-polar stationary phase, which is a C8 column, you can see that the aliphatic hydrocarbon chain is constituted by 8 carbons. The total of 8 carbons which is bonded to the silica. So in case of C8 column, you find silica bonded octyl group that is constituted by 8 carbon atoms. And hence the stationary phase is non-polar in nature. And through this non-polar stationary phase, I mean the Hplc column containing the non-polar stationary phase, which could be either C8 or C18 material, polar mobile phase flows through the column under high pressure. Some of the common polar solvents recommended for the Hplc technique, that is reverse phase Hplc technique, are methanol, water and acetonitrile. The drugs of pharmaceutical interest like paracetamol, amino acids like glycine and sugars like glucose can be effectively separated by reverse phase HPLC technique. Now rule of thumb, like attracts like, polar molecules will have greater affinity for the polar mobile phase and interact via hydrogen bonding or dipole-dipole interaction and elute faster from the column along with the mobile phase. They interact weakly with the non-polar stationary phase. Now in case of testosterone molecule, which is highly non-polar in nature, it will strongly interact with the non-polar octyl chain in case of C8 column by van der Waals interaction, while in case of polar molecules like paracetamol, because of their highly polar nature, they interact strongly with the polar mobile phase via hydrogen bonding or dipole-dipole interaction and hence are eluted faster. So non-polar molecules, they interact via van der Waals attraction, like in case of testosterone molecule with the non-polar stationary phase, while polar molecules like paracetamol, they interact with the mobile phase or even with the stationary phase depending on the technique employed by hydrogen bonding or dipole-dipole interaction. So the polar molecules, they interact with either the stationary phase or the mobile phase via hydrogen bonding or dipole-dipole interaction, while the non-polar molecules, they interact either with the stationary phase or the mobile phase via van der Waals interaction. So the principle of the HPLC technique is adsorption of the molecule onto the solid stationary phase depending on their relative affinities. So it is not that the molecule being separated by HPLC technique is interacting only with the stationary phase. It is also interacting with the mobile phase. So to what extent the molecule interacts with the stationary phase or the mobile phase decides the time taken by the molecule to elute out of the column. Now here we have a non-polar mobile phase. hexane and a polar stationary phase. That is in case of silica column. The non-polar mobile phase flows through the column. The molecules that are sandwiched between the stationary phase, polar stationary phase and the non-polar mobile phase, they travel with varying speeds. Polar molecule travels a shorter distance. Molecule of intermediate polarity travels further ahead of the polar molecule, while a complete non-polar molecule like naphthalene, it covers a longer distance. It travels a longer distance because of the van der Waals interaction with the non-polar mobile phase. So a non-polar molecule like naphthalene interacts with the non-polar mobile phase via van der Waals interaction. And as a result, the naphthalene molecule, it is carried away through the length of the column at a longer distance along with the mobile phase by van der Waals attraction. While polar molecules like paracetamol, it interacts via hydrogen bonding with the polar silanol groups, and therefore they are binding strongly to the polar silanol groups and they are retained in the column for a longer period of time. While the molecule of intermediate polarity like acetophenone, it interacts with the polar silanol groups via hydrogen bonding, but the extent of hydrogen bonding is less as compared to that of paracetamol because there is only one atom available for hydrogen bonding, that is oxygen atom. So it is not that they are capable of interaction with the station phase only via hydrogen bonding. They are also capable of interacting with the mobile phase, non-polar mobile phase hexane via van der Waals attraction because of the presence of lipophilic aromatic ring, both in case of acetophenone as well as paracetamol molecule. So as the non-polar mobile phase, it flows through the column. The molecules, they are dragged by the mobile phase to various distances of varying length. So this depends on the polarity of the molecule. So with the flow of the mobile phase through the column, the components, they travel at varying speeds. So you can see that hydrogen bonding, it decreases as you go down the column, while the van der Waals attraction increases. So it will be the non-polar naphthalene molecule that is coming out of the column first as it interacts strongly with the non-polar mobile phase hexane via van der Waals attraction. This will be followed by acetophenone molecule, which is of intermediate polarity, and the molecule that is finally eluted out of the column is highly polar in nature, that is paracetamol, and will be eluted last. So here we have the polar stationary phase with polar silanol groups. Let's say the acetophenone molecule labeled as A, it is binding strongly to the polar silanol groups via hydrogen bonding by adsorption. At the same time, the non-polar mobile phase, it is flowing through the column. With the solvent flow, the non-polar mobile phase, it is displacing the adsorbed molecule A onto the polar silanol groups, and this is called desorption. And again, after a short period of time, again the molecule is adsorbed onto the polar silanol groups by adsorption. Now this cycle of adsorption, desorption and adsorption, it continues until the component or the molecule is eluted out of the column. So the non-polar mobile phase, that is hexane molecules, they compete and interact effectively with the non-polar unlike, that is acetophenone molecules, and displace these unlights from the stationary phase sites to which they are strongly bonding to, causing them to move faster through the column, and hence they are weakly retained. So in the polar stationary phase, you find the polar silanol groups. That is tightly packed into the column through which the non-polar mobile phase flows through. Now the components, they travel at varying speeds depending on their relative affinity toward the stationary phase. So a polar molecule, it strongly interacts with the polar solenoid groups, while molecule of intermediate polarity, it interacts moderately, while a non-polar molecule, it interacts weakly with the stationary phase. It interacts strongly with the non-polar mobile phase via van der Waals attraction or interaction, and hence eluted out of the column first. So rule of thumb, always remember this: like attracts like. A polar molecule is attracted by a polar stationary phase, while a non-polar molecule is attracted by a non-polar mobile phase. Now in a normal phase HPLC technique, stationary phase is polar, for example silica column. Mobile phase is non-polar, example hexene. Now let's try and separate amino acid mixture containing glycine, alanine and phenyl alanine. So we take a polar silica column bearing a polar stationary phase, and we use the non-polar mobile phase hexene, is flowing through the column, and three amino acid molecules, they are sandwiched between the polar stationary phase and the non-polar mobile phase in the column, and the relative speed or the distance traveled by these three molecules depends on their relative affinities towards the stationary phase or the mobile phase. So a polar molecule like glycine, it strongly interacts with the polar stationary phase and hence retained for a longer period of time, and hence eluted last from the column. Alanine, which is of intermediate polarity, it moderately interacts with the polar stationary phase and eluted second from the column. While a non-polar molecule like phenylalanine, it weakly interacts with the polar stationary phase and eluted first from the column. Now in case of reverse phase HPLC technique, the stationary phase is non-polar, for example C8 column. Mobile phase is polar, for example water and methanol. Now let's try and carry out the separation of the same amino acid mixture by adopting reverse phase technique and see what will be the end result. So here in the reverse phase HPLC technique, the stationary phase is non-polar, and in this column containing non-polar stationary phase, the polar mobile phase, it flows to the column under high pressure. So we have a C8 column for the separation, which is acting as a non-polar stationary phase. So it is called C8 column because of the aliphatic hydrocarbon chain constituted by 8 carbon. And in case of C18 column, it will be 18 carbons. That's the only difference. And through this non-polar column containing non-polar stationary phase, the polar mobile phase flows through the column, and we are employing the polar solvent combination methanol and water for the separation. Now the three amino acid molecules glycine, alanine and phenylalanine, they travel at varying speeds, and the distance traveled by these molecules of varying polarity depends on their relative affinity towards the non-polar stationary phase and the polar mobile phase. Now in case of glycine, it strongly interacts with the polar mobile phase via hydrogen bonding or dipole-dipole interaction. So all three molecules, all the three amino acid molecules. So amino acid molecules are characterized by presence of polar amino and carboxyl groups. So all the three molecules interact with the polar mobile phase via hydrogen bonding or dipole-dipole interaction. But at the same time, they also interact with the non-polar mobile phase constituted by 8 carbons present in the aliphatic hydrocarbon chain of the non-polar stationary phase. That is by van der Waals interaction or attraction. So in case of glycine, you find the methylene group which weakly interacts. In case of alanine, you find the non-polar methyl group which moderately interacts with the non-polar hydrocarbon chain. While in case of phenylalanine, the aromatic ring it interacts strongly via van der Waals attraction. So in case of glycine, the interaction of the polar groups with the polar mobile phase dominates, while in case of phenylalanine, the van der Waals interaction with the non-polar side chain or the stationary phase, it dominates. So rule of thumb, like attracts like. In case of phenylalanine, you find the dominance of non-polar interaction between the aromatic ring and the non-polar side chain of the stationary phase. And therefore, the non-polar phenylalanine is retained in the column for a longer period of time and hence eluted later out of the column. While glycine molecule, which is highly polar in nature, it interacts with the polar mobile phase via polar-polar interaction. So hydrogen bonding wins the competition and glycine is attracted to the highly polar mobile phase. It dissolves in the polar mobile phase and eluted out of the column first. So hydrogen bonding wins or dominates over the van der Waals interaction. That is in case of glycine molecule. While in case of phenylalanine, the van der Waals attraction, it wins the interactive forces and ends eluted later out of the column. So the distance or the speed covered by the molecule, it is governed by the dominance of either van der Waals attraction or the hydrogen bonding or dipole-dipole interaction. Thank you so much for watching my video. I hope you enjoyed it and I'll meet you in my next interesting tuning session.